Hi guys, we're gonna continue on with units of pressure. I wanna go back and talk about the barometer and the manometer, and then we'll quickly talk through all of the gas laws. And then after we do the gas laws, we'll talk about Dalton's law of partial pressures, as well as going back through and deriving that formula for density based on the ideal gas law, because you did that today in your POGL, but I want to make sure that every group is solid on how to derive that, because I will ask you to do that on a quiz maybe, or on a test. Okay, so units of pressure, we know that 1 atmosphere is equal to 760 millimeters of mercury, and that's equal to 760 torr. And that's also equal to 101.3 kPa. So Pascal is usually the type of force that we're going to talk about, or the unit of pressure that we talk about when we're finding a specific force that's in a given area. So we typically will use pascals when you're given force and then you're given that surface area. So like if we were finding the pressure that is exerted on your foot or on your calf muscles when you're wearing heels. Another type of pressure that's kind of not commonly used is a bar. I don't know that you'll see that so much on your AP test, but just that we know that 1 bar is equal to 100 kilopascals. Okay, we can measure atmospheric pressure based on using a barometer. The barometer was developed by a scientist named Torricelli, and ultimately what happened was Torricelli had just a little bowl of liquid mercury. In this container of liquid mercury, he also included an empty or vacuumed long cylindrical tube, and that was empty at the time. Whenever he inserted this vacuumed column into that container of mercury, the atmosphere can exert pressure on the mercury that's exposed in this container. And when it does that, the atmosphere will then push up mercury into this column that's vacuumed out. So I can measure then the height of this mercury, and that particular height is going to give me how much atmospheric pressure there is within a day. Since he used mercury and since the column was calibrated in millimeters, we have a unit of pressure that he developed, Torricelli, that was called millimeters of mercury. So that's the reason that we get that name. Also, he called it torr, so those two are interchangeable because Torricelli is the person that created the barometer. And this was done in around the 17th century that he did this. Let me get this off of your page here. Perfect. Okay, so he said that 1 atmosphere was going to be equal then to 760 torr, which is also going to be equal, like we already said, to 760 millimeters of mercury. So at standard pressure, normal atmospheric pressure at sea level is referred to standard pressure. So standard pressure we're going to see as 1 atmosphere, or it could be any of the ones that we've already talked about. Oh, sorry. These are some conversion problems. So if you would like to try to convert, you are more than welcome to practice these, but I know that you're all pretty good with dimensional analysis, so I think that you can do them. But if you want to do them and then check, I'm happy to check them for you. Okay, manometer. Let's talk about the manometer. A manometer is used to measure the difference in a specific gas versus atmospheric pressure. So a manometer is something that has an open end and then something that will have a sample of gas with a closed end here. So my sample of my gas is over here in the valve, and then the atmosphere can be pushing down in here. In a manometer, to understand how much the gas is pushing and then how much the atmosphere is pushing, we always add in a sample of liquid, and usually that liquid is going to be mercury. So I can tell the height difference, and I can see how much each gas is pushing on based on the difference in height between the gas here and then the atmosphere pushing on that liquid. So when I open the gas valve, this gas is going to come through the U-tube. So in a manometer, I have my valve, I have a U-tube, and that one end of the U-tube is open because that allows the atmosphere to push in on that liquid mercury. As the gas continues to go out, it will push on the liquid. I can see here that then the difference, so I'm calling that height, this difference in height, I'm going to call that P sub H. That's going to be the pressure that is exerted within this height. Atmospheric pressure is going to be here, and then I can find the pressure of the gas by taking the atmospheric pressure plus the pressure that is specific for this particular height of that liquid mercury. So it's only used whenever I'm trying to find the pressure of a gas. And I usually know the sample of the gas, so just knowing atmospheric pressure, which I can look online at any like WeatherBug, anything like that. So it's something that's always known. And then I can measure this, so I can always find pressure of the gas that way. So let's see what an example of that would look like. So it says, on a certain day, the atmospheric pressure is 764.7 torr. A sample of gas is placed in a flask attached to an open-end mercury manometer. The heights are given in the figure to the right. What is the pressure of the gas in the flask in atmospheres, and then what is that pressure in kPa? Okay, there we go. So I don't think we could see all of that. So I'm going to use that formula that we just looked at. I'm going to look at the formula that we just looked at, which is the pressure of the gas is equal to the atmospheric pressure plus then the pressure specifically with that liquid mercury. So let's open up an Active Inspire. Okay, so I have pressure of the gas is equal to atmospheric pressure plus the pressure and the height of that liquid mercury. Okay, atmospheric pressure, they gave me that value in the problem. They told me on a certain day the atmospheric pressure is 764.7 torr. I'm going to go ahead and just say that that's the same thing as millimeters of mercury. And I'm going to say that because the height difference here is in millimeters, and I know that that's of mercury. So because of that, it's just easier for me to make this as millimeters of mercury since this is in millimeters of mercury. So I'll do 764.7 millimeters of mercury plus okay, and then plus the difference in these, because ultimately this is going to be exerting the same pressure here. So I want to know the pressure that's going to be exerted in this difference here. So I'm going to do 136.4 millimeters of mercury minus 103.8 millimeters of mercury. And that's going to be the pressure for that height. So let's do 136.4 minus, I think it was 103.8. And that's millimeters of mercury there. Okay, and if I add those together, I'm going to get the pressure of the gas to be 797, 0.3? And then that'll be millimeters of mercury. But they asked me for my answer in atmospheres, and then they also asked my answer in kPa. So if I have 797.3 millimeters of mercury, I want to convert that into atmospheres. So in 1 atmosphere, I know there's 760 millimeters of mercury. So we'll just do some dimensional analysis here. And then I should get that in atmospheres to be 1.049 atmospheres. Okay, but they also wanted it in kPa. So then I'm going to take that 1.049 atmospheres, and in 1 atmosphere, there's 101.3 kPa. So if I took that, then I should get 106.3. And that'd be kPa. Perfect. So I've not seen a question doing mathematical things with a manometer. I think for the most part they just want you to know what it is, kind of how it works. But just in case, I want you to know that equation that's down below there with it, okay? So the equation right here, that to find the pressure of the gas, it's going to be equal to that atmospheric pressure plus the addition of the pressure that's being acted on with the liquid mercury that's in the U-tube. Okay, so in your POGL, we focused on all of those gas laws, and you've been deriving some things for me in the POGL. You derived the density equation for me today in your POGL. And then I think the last thing that we kind of ended on was with Dalton's law of partial pressures. We just didn't name it, I think, in your POGL. So let's go through all of those. So in gas laws, there are 4 variables that we need to define the physical condition or state of a gas. Those variables are pressure, temperature, volume, and number of moles. So everything in the ideal gas law is one of the variables that we need to define the state of a gas. If some of those things are constant, that's where we're going to see our different gas laws. So for example, our pressure-volume relationship is Boyle's law. We know that Boyle's law is just P1V1 equals P2V2. And we saw today in class that we're using ideal gas law, and if I'm just thinking about how temperature and how number of moles stay constant, then that R, N, and T are going to just be, I'm going to symbolize that with K. So remember, we have P times V equals K. So I can derive that based from ideal gas law, and we've done that today, and you need to be able to do that as well. So I can see that as the balloon rises, as it's rising through the atmosphere, I see that the volume of the balloon gets larger. But why does the volume of the balloon get larger? As the balloon moves up into the atmosphere, pressure becomes lessened. So as pressure lessens, volume is going to increase. So pressure and volume are inversely proportional quantities. So it says the volume of a fixed quantity of gas at a constant temperature is inversely proportional to its pressure. I can see that if we graph volume and pressure, it is not a linear relationship. But if I graph volume over volume versus 1 over P, I see that that is then going to be a linear relationship. So a plot of just volume pressure gives me that curve, but a plot of volume versus 1 over pressure is going to give me that straight line. So this is what we derived, or what we saw today, from the ideal gas law, and then I'm just going to rearrange that and say one of those variables is going to equal this, and that's the relationship between those two variables. So they are inversely proportional. Okay, Charles' law is about volume and temperature, where everything else will stay constant then. So a volume of fixed amount of gas at constant pressure is directly proportional to its absolute temperature. Okay, so if I increase temperature, then that means that I'm increasing the kinetic energy of those atoms that are in that sample. Because I'm increasing their kinetic energy, I'm increasing their movement. They're able to have more collisions, and those collisions will happen more frequently. So because of that, pressure should go up, because pressure is really then just going to be based on how much force is being exerted based on their collisions. So because I'm increasing temperature, pressure has to increase as well. So that means V over T is equal to K, and a plot of volume versus temperature will give us that straight line. So we should be able, like I said, to derive this from ideal gas law. I also should be able to distinguish whether volume temperature would give me a straight line, which it does, versus pressure volume. It's going to be volume with respect to 1 over pressure, okay? That would be what would give me a straight line. Avogadro's law is about volume and number of moles having a relationship. So ultimately, Gay-Lussac is the person that really, I think, experienced all of these things, and then Avogadro just kind of took it. So I think we may get to Lussac's law next. But Avogadro's law is going to be between volume and number of moles. So the volume of a gas at a constant temperature and pressure is going to be directly proportional to the number of moles of that gas, okay? So as long as, if I'm looking at, here's helium, here's nitrogen, and then I have CH4, which is methane. So all of my volumes are the same. At 22.4 liters, I see all of these are the same. And then if the volume is the same, they're at the same pressure, let's say that stays constant, temperature stays constant, then the number of the gas molecules, number of moles, should be proportional then to the volume. Gay-Lussac's law. What variables are related in Lussac's law? That's going to be pressure and temperature. So it's very similar to Charles' law in that Charles is V over T. Gay-Lussac's law is going to be P over T. What variables are going to remain constant? We already know if it's between pressure and temperature, then volume and number of moles stay constant. The mathematical equation is P over T equals K, and that's also going to be a direct relationship. So as pressure increases, temperature is going to increase. Just like in Charles' law, as temperature increases, volume is also going to increase. Makes sense? I have more collisions, so that means that I have something that can expand out in a larger area. Okay, I want to skip this for right now because you've already been doing this in your POGIL, and you've all been doing a great job. You also have been doing these gas law problems in your homework that you had over the weekend. So ideal gas equation, so far we've seen Boyle's law, which volume is proportional to 1 over P. We've seen Charles' law, which volume is proportional to temperature. And I've also seen Avogadro's law, in which volume is proportional to number of moles. So if I combine all of these together, I get volume is proportional to number of moles and temperature over pressure. So if I also know that there is a constant of proportionality, kind of keeps everything on an even keel. And we already know that that gas constant is called R. Those are all of the numerical values that it can take on. This will be given to you on your AP chemistry test on that constants page. I will also give that to you on any test or quiz that you have in here. So the relationship here that we just said, volume is proportional to number of moles and temperature, but inversely proportional to pressure. I'm going to include my gas constant, which is now R. So all I'm doing is saying that my volume is equal to R times what I had here from up above, or we rearranged it to be PV equals nRT. So there's our ideal gas law. So what is an ideal gas? Ultimately, we are going to assume that everything acts like an ideal gas unless they tell you otherwise. So an ideal gas is just a hypothetical gas whose pressure, whose volume, whose temperature, all can be described using the ideal gas law. An ideal gas must obey that PV equals nRT. If it doesn't obey that law, then it's not an ideal gas. So when we derive that ideal gas law, we like to assume several things. And one of those assumptions is that the molecules of an ideal gas do not interact with one another at all, meaning that they're not going to attract one another, they don't repel one another. If they do come in contact, they're going to hit, and then they're just going to bounce off. So it's in completely elastic collision, meaning that they just hit and they bounce right off, and there's no really exchange of energy there. Okay, another thing that we assume is that the combined volume of the molecules is actually much smaller than the volume that the gas occupies. So we like to consider that the molecules taking up, the molecules that are in whatever sample of gas we're talking about really just take up no space at all in the container. So their mass is negligible, is pretty much what we're saying. And all of these things are also assumptions that we make for the kinetic molecular theory, which we'll get into a little bit in the video. Okay, so ideal gases versus real gases. The ideal gas law can account for properties that we see in most gases. So most gases actually do behave like ideal gases, but there are definitely some things that don't account well for all gases. So although real gases don't always behave ideally, their behavior differs so little from an ideal gas that we kind of ignore a lot of deviations that we see. As we can see here, this is I see that an ideal gas, if we're thinking about at these standard conditions, we know that for volume, we think about them as being that 22.4 liters in 1 mole. And that's just something that we know that happens at standard temperature and pressure. So if I compare that to gases that I see on this chart, chlorine is about 22.06 liters, and these are just taking into account the real gases. Carbon dioxide is 22.31. Ultimately, the graph is showing us that all of them are in comparison to that ideal gas at standard temperature and pressure being 22 or being able to be measured at 22.4 liters at STP. So even though we experience real gases, a lot of them will really truly behave like an ideal gas. Okay, these two problems are just using the ideal gas law. I am skipping them because you have already been doing this. So we can skip over since you're already pros at this. This is the exact same thing. We're just doing more gas law problems, and I think that you've done enough of those problems. Okay, today in your POGIL, I think every group went through and we tried to derive how I could get density based on the ideal gas law, okay? So when we found density from the ideal gas law, I think I tried to talk through with most groups that we really want to think about N. So I'm given PV equals nRT. I rearrange this here so it's N over V equals P over RT, and I just did that because I know that moles has a relationship with molecular weight, just like it has a relationship with mass, with grams. And my goal is to show that density equals something with the ideal gas law. So for N, number of moles, I could find mass using moles by taking the number of moles times the molecular weight, and that would give me mass. So if I do that, I can see that here, that moles times molecular mass is equal to the mass. Now in what we did today, let's kind of look at it as how we, I think, looked at it today in our groups. So we have PV equals nRT. And I know that N is really just number of moles. And if I took mass over molecular weight, then that would give me moles. And I know that because mass is measured in grams and molecular weight is measured in grams per mole, which then would just give me moles, which is N. So I want to substitute this in for N. And I'm going to call mass just M, and we'll call molecular weight just the way that it is there, MW. So then that would give me PV equals MRT over MW, which is molecular weight. Okay, if I rearrange and kind of move this around a little bit, I want to get M over V on one side because I know M over V is density. So if I do M over V, then that's going to equal pressure times molecular weight over RT. So since M over V is density, we're going to go up. Density equals pressure times the molecular weight over RT. So that's how I can calculate the density of a gas based on the ideal gas law. Okay, so if we go back to our slides, in your notes, ultimately we did the exact same thing, only in your group, in your POGL, you did it for me instead. So I substituted some stuff in here. I said capital M was molecular mass. In your POGL, we did MW, just means molecular weight, but it's the exact same thing. So then I just rearranged. I got M over V equals pressure times molecular weight over RT, and we just derived that on the Promethean board. So then instead of saying M over V, we're going to call that density. So density equals pressure times molecular weight over RT. So I really only need to know pressure, temperature, and the molecular mass of that gas, so that way I can find the density. Okay, we can also manipulate density. So let's say that I don't ask you to find density. Let's say I ask you to find the molecular mass of a gas. If I rearrange that, I get molecular mass is equal to the density times gas constant times temperature over P. Or I like to think of it as dirt over P. So if you want to find molecular mass, it's dirt over P. Guys, these problems here are just you utilizing density is equal to our calculated one for density, which is P, pressure times molecular weight over RT, as well as the molecular mass one that we just did, which is dirt over P. You've done this today in your POGL, and you've been doing this. I know you guys can math. It's literally plug and chug, so we're going to just skip over that, okay? Dalton's law of partial pressures. So I think in your POGL, this is kind of where we got to today, and then time ran out, so we had to stop. So Dalton's law of partial pressures is that the total pressure of a mixture of gases equals the sum of the pressures that each of those gases would exert if they were just present alone. So in other words, all we're doing is going to add up each of those individual pressures, and then the pressure of that mixture is going to be the total. So total pressure equals the pressure of each one of them just individually. Okay, so in class tomorrow, this is where I would like to start. We'll do some practice problems with calculating partial pressures. So our goal tomorrow is to start here. We'll talk about the kinetic molecular theory tomorrow, talk about all of the assumptions and then how to apply it. We'll talk about Maxwell-Boltzmann's distribution as well as molecular speeds and then how we can calculate those. And I'll also probably give you some practice multiple choice questions over chapter 10 as well as chapter 5, so that way we can kind of bridge all of these two things together. If you have any questions, let me know, post on your blog or just shoot me an email. I'll be in class for most of the night, so I'll have my computer right next to me. So feel free to email me if you have any questions at all. Have a really wonderful night, guys. I'll see you tomorrow. We have one more day and then it's Thanksgiving. Whoop, whoop!